We're continuing our work with inferential statistics, which is that idea of what does our sample proportion tell us about the population proportion. So with hypothesis tests, what we'll be doing is we'll have some sample statistic, and then we'll be using that to see if there's evidence to show that the population is actually incorrect, that our value has significantly increased or decreased or just changed. So we're trying to use our sample statistic to prove something about our population proportion. So in this video, what we're going to do is just a little introduction. I'm going to run through kind of the setup and the process for these hypothesis tests, as well as some key ideas. Just keep in mind, with the hypothesis test, we're going to end up with this 5-step process. So in this video where I'll show you all 5 steps, if it feels very overwhelming, don't worry. The next videos will go way more into depth in terms of step by step what we're doing and more into the ideas behind what we're doing. So with this, I'm going to introduce us with a fairly simple scenario of just flipping a coin. So when we flip a coin, we assume it's 50-50, so 50% chance of heads, 50% chance of tails. What we're going to look at is, what if I flipped my coin 50 times and I saw 75% heads? So the idea being, if I did this, that seems like a very large percentage of heads. Now, is it impossible? No. But what it might make me wonder is my coin unfair? Is my coin weighted to show heads more of the time, significantly more than 50%? So what we want to do is see, is this evidence that the coin is unfair or showing heads more than 50% of the time? So in terms of the idea of evidence, when we collect evidence, we want to talk about this phrase, statistically significant. Because in terms of the setup here, if I'm just asking if heads is showing up more than 50% of the time, well, yes, 75% is more than 50%. But is it significantly more than 50%? So this is where we're going to bring in ideas from sampling and our sampling distributions to understand how does our sample compare to how other samples would behave. So let's break down some pieces here. First off, what we need to start with our hypothesis test is, what are we assuming is true? So like I've said with flipping a coin, we assume when we grab a coin, we would assume it's a fair coin. So we're starting with this assumption, and the assumption would be that we have a fair coin, that it's showing heads 50% of the time. Now, this assumption that we're going to be stating, this is called our null hypothesis. It's what we assume is true for the population, or it operates under the idea that nothing has changed. When I grab a coin, it has this 50% chance. For notation with the null hypothesis, how we denote it is with a capital H with a subscript of 0. So that would be our null hypothesis. So when we get to hypothesis testing, what I would actually write here in terms of notation is that we're going to assume, so my null hypothesis would be, and then we're going to talk about this proportion. And the hypothesis test that we do is only going to be in terms of a single proportion. So what I'm interested in here is this proportion of heads for my coin. And my assumption is that the proportion of heads is 50%. So for my null hypothesis, what I would write is that this proportion is just equal to 0.5. So that's my assumption. This proportion of heads is 50% for my coin. Then what we have is this other hypothesis of what we want to prove. So what I want to prove, or what I want to find evidence for, is that it is unfair that I'm seeing more than 50% heads. So I want to prove that I have an unfair coin, which means significantly more than 50% chance of heads. So this is where I want to show how things are changing. How is my sample going to prove some sort of change from our assumption. So this that we're going to state here is called the alternative hypothesis. And for notation, what we'll use here is a capital H with the subscript of capital A. So for my alternative hypothesis, what I'm trying to prove here is that this proportion of heads is significantly more than 50%. So I'd be trying to prove that this is larger than 0.5. And in the next video, we'll talk much more about how to set these up and kind of how to get from the wording to setting these. But I just kind of want to show you the notation and the ideas behind it here. All right, so we assume we have a fair coin, but what I want to prove is that the coin is unfair and showing heads more than 50% of the time. So what I need to understand is that if it's a fair coin, if my assumption's true, then if I flip a coin 50 times, how do samples behave? So how would a fair coin flipped 50 times behave? This is where I need a sampling distribution of proportions. And for the sampling distribution, I'm going to build it around the null hypothesis. So I'm going to build it around my assumptions true, the fact that I would assume that I'm flipping a fair coin. So I need a sampling distribution built around the null hypothesis and our sample size of 50. The idea being I want to see a distribution for how various p-hat values, how different sample proportions would behave if it's a fair coin flipped 50 times. So as a reminder of some things that are going to come up here is that we should always check the central limit theorem first. So that'll be something that pops up. And then for setting up the sampling distribution, your mean is just equal to the proportion. So for us, it'll be that proportion from the null hypothesis. And then standard deviation will be the square root p times q over n. But what this will give us, and I'll plug in the actual values on the next page here, where I'll actually go through the full hypothesis test for this. But just to give you an idea of what we're trying to get at is with the sampling distribution, and this will be built around the idea that we expect 50% heads, then we can see how p-hat behaves for a fair coin flipped 50 times. So then we get this idea of what are likely outcomes in terms of flipping a coin 50 times, and then what are unlikely outcomes. So once we get this distribution, then what we can do is see where does our sample land. So we have this idea of how a fair coin flipped 50 times behaves, and then we want to see how does my sample land in comparison. And this is where we could branch off into two cases. So when we get to conclusions for these hypothesis tests, there's going to be two possibilities. Like in this case, it would be that I have proven that I have an unfair coin, or the other case will be that I haven't proven that I have an unfair coin. So we either have evidence or we don't have evidence for what we're trying to prove. Or what it comes down to is we'll have evidence for the alternative hypothesis, or we will not have evidence for the alternative hypothesis. Something I'll emphasize when we go through this more is that we aren't proving that we have a fair coin, and we're just trying to answer this question of, is there evidence that the coin is unfair? And it'll either be essentially a yes or no. Yes, we have evidence, or no, we don't have evidence. So that's where it splits into these two cases. So what could happen is we build the sampling distribution around that null hypothesis. So assuming that we have a fair coin, so expecting 50% heads. And what this case would look like is that when we then go to compare where our sample statistic lands, maybe it's way out here in the tail, somewhere very unlikely. versus the case where the probability of that occurring is not small, which would be if we have our sampling distribution built all around a fair coin, seeing 75%, maybe it lands closer by with a more likely outcome. Now, in terms of probability, as we've talked about before, with the normal curve, we can't find the probability of just a single line. It would just be 0. So what we do here is the probability that we want to analyze is the probability of that sample statistic or more extreme. So it's like, what's the probability of getting 75% heads or even more heads? So 75% or more. And same thing over here, what's the probability of getting 75% or more? So this is where we need to see that sampling distribution so we can see where are we landing. Was getting 75% very extreme? And this is where we start seeing something that's statistically significant because we basically get this sample that was so unlikely. So this would translate to our sample statistic. Our sample that we collected was unlikely. It was even very unlikely. We could go and emphasize it even more. But we have this unlikely outcome under the assumption. So under that null hypothesis, we're seeing something extreme occur. We're seeing something that was close to impossible happening, which means that's statistically significant. The idea being, if I had a fair coin, to get 75% out in this scenario would be so unlikely, which starts to build evidence for the idea that I don't have a fair coin. So if I go back to my hypotheses and I'm starting to build this evidence that I don't have a fair coin, what I want to do is essentially scratch out the assumption. I want to say that's not happening here. We're getting evidence that this is true because we saw an outcome that was so unlikely if this was true. So we built everything around this idea of having a fair coin, and we just saw something that's near impossible for a fair coin to do. Now, we'll talk about how there's this little chance of error here, like it's not totally impossible for this to happen, but to take a random sample and see this occur, very unlikely. So what we're going to do is the phrasing we'll use is we say we reject the null hypothesis. So we're going to reject that null hypothesis because essentially what's happening here is the curve that we drew here represents the null hypothesis, and we saw something pretty much impossible underneath that curve. So then what we're building here is evidence for the alternative hypothesis, which is exactly what we want. This is the case that we look for when we do these hypothesis tests. We essentially want to find this low probability because then it's giving us evidence for what we're trying to prove. So this would be a case where we'd end everything by saying we have an unfair coin. There is evidence, there's statistically significant evidence that we have an unfair coin because if our coin was fair, our sample was basically impossible or close to impossible. Now, what's happening in this scenario, when the probability is not small, is that getting that 75% heads out is fairly likely if we're assuming we have a fair coin. So this would be a case where our sample was somewhat likely under the assumption that we have a fair coin. So basically getting 75% out just by random variation is a somewhat likely outcome. So this would be a case that is not statistically significant, because we basically saw something that could happen with a fair coin. So with that, in terms of looking at our null and alternative hypotheses, and with this assumption that we have a fair coin, we can't throw that out. Even though we saw something that was larger than 50%, it wasn't significantly larger than 50%. So we can't reject this idea that we have a fair coin. We haven't proven that we have a fair coin. We want to be very careful of that. We didn't prove this, but it's just that we can't throw that idea out. So the phrasing that we use here is that we failed to reject the null hypothesis. We didn't have strong enough evidence to reject that null hypothesis, which means in terms of evidence for the alternative, it's just not strong enough evidence. Even though, again, it's definitely more than 50%, it's just not significant enough. So what we have is not sufficient evidence for that alternative hypothesis. So at this point in our hypothesis test, we end up with these two branches, and it all comes down to that probability that's being calculated. And what we'll do is once we get that probability, it's just an analysis of whether that probability is small or large. Again, we'll talk about what the cutoff is for that. But this probability is so important. So we have a name for this specific probability that we're finding. This is called the p-value. So the p-value is going to be this probability of seeing our sample statistic, or more extreme, under that null hypothesis. So when we get this p-value out, there's going to be these two cases of the p-value is small versus the p-value is not small. And then depending on which case we have, all of these pieces fall through. And in terms of wording our conclusion, which I'll show you an example of that on our next page here, we want to put in terms of whether or not we have this evidence for the alternative hypothesis. All right, so now that we kind of went through the abstract behind it, I'll show you the actual steps that we go through here. So setting up the null and alternative hypothesis, this first step that we'll do. So null and alternative hypotheses, and I'm just going to copy what I actually wrote up above there, which is that we're assuming this population proportion is 0.5, and we want to prove that it's more than 0.5. So in this first step, we're just going to outline what we assume is true and what we want to prove. Our next step is going to be to check the central limit theorem to make sure that if we're working with this sample size and working with this assumption, will we have a bell-shaped curve out? Because the bell-shaped curve is important for calculating probability in this last step here. So checking the central limit theorem, we're going to check for independence, randomization, and success failure. So again, with independence and randomization, we'll be good there. Flipping a coin is independent. The probabilities don't change. Randomization, we chose a random coin, so we'll call that random enough. And then success failure, everything we do from here on out is pretty much built around this null hypothesis. So that's going to be a proportion. The proportion that we use for checking this success failure. So what I'm going to do is take 50 times that proportion of 0.5, and then you do 50 times 1 minus that proportion, which when it's 0.5, it's just the same thing. Both of those are 25, which are both more than or equal to 10. So we're all good to go there. So we need to check the central limit theorem to make sure we have a bell-shaped curve. So what we're going to do here is build our sampling distribution. So we need our mean and standard deviation. So the mean of our distribution, so it's always going to be centered around our assumption. So going back to the null hypothesis, it's going to be centered at 0.5, since that's what we would expect to come through from our samples. And then for standard deviation, square root of 0.5 times 0.5 over our sample size of 50. And that's going to give us a standard deviation of 0.0707. Now, a little side note here, and I'm going to do this throughout the videos just because a lot of resources use this test statistic, which is just a z-score. And I'll show you how that comes through in terms of finding p-value and probability. There's basically two ways to do this. Whichever way you like better, it's not a huge difference between them. In fact, they'll give the same exact answers out. But I'm going to show you both, but I want to emphasize this terminology of test statistic, even though we do kind of have this workaround and we could skip it. It's a term that comes up a lot in homework, math, and then especially other textbooks and resources for studying. You'll see this z-score come up. So this z-score comes down to basically a z-score for our sample statistic. So we have this sample statistic of 0.75. So what we would do here for making the test statistic is we want to see how does that sample statistic compare to what's expected, and you can use this mean and standard deviation here. So how does it compare to the center of the distribution divided by the standard deviation of this distribution? So what we could do is make this z-score and get an idea of how extreme our sample is. So comparing it to the 0.5 and then over the standard deviation of 0.0707. And that z-score in this case would be a 3.5361. Which again, in terms of unusual z-scores, it's usually over 2 away. So this could give you a glimpse into, this is an unlikely scenario. This 75% occurring in terms of it as a sample, unlikely. But this test statistic is a way to get an idea of that. All right, so calculating the p-value, and this will have I'll show you both ways of how you can go about this. I'm going to use just directly that sampling distribution that we made. So centered at 0.5, standard deviation of 0.0707. And what I want to do to find p-value is like what I drew up above there in terms of with this sampling distribution, I want to see where does 0.75 land. So I know it's somewhere over here to the right. I could make a more detailed number line with that standard deviation, but in terms of a general idea, I want to see where's that 0.75 land and what's the area to the right. And that area to the right is my p-value. That's the probability that I'm interested in. So with this, to find my p-value, we have to go to GeoGebra. And this is a good thing to keep in mind. Every time you need a p-value, you'll be in GeoGebra or whatever technology you're using to find probability. So let's go over to GeoGebra and set up my distribution. So 0.5 for the center, and then 0.0707. And then I want an area to the right, and that cutoff is going to be a 0.75. And what you can see is with this number line, 0.75 is way out there as a sample, which lines up with what we were seeing with that z-score coming through. So this p-value is the probability, so we're going to grab that 0.0002. So the other way you could have done this, alternatively, is you could have done this using the test statistic. So using a sampling, that standard normal distribution. It's been a while since we talked about that. So standard normal, mean of 0, standard deviation of 1. And if you go in there and use that distribution, so centered at 0, and then looked for this probability of 3.5361 or larger, let's see what happens when we do that. So set my mean of 0, standard deviation 1, and then area to the right of 3.5361. Nope, wrong spot. Sorry about that. 3.5361. Same exact answer. So this is where there's two ways to get the same answer. I'm mostly going to stick with this first way that I did just because I like it keeps everything in context. You can see the value that we assume is true. You can see where our sample lands in comparison. And while that's being shown here as well, it's a little taken away from context by switching things into z-scores and standard normal. So if you have a preference, either way works. Both of them will get you to the same p-value. So we have this p-value. Now that is very small. That is a very low probability of occurring. And how this would translate, the idea is that if the coin was fair, so if our assumption is true, which is basically what this bell-shaped curve is showing here, so if we have a fair coin, there is and this is a probability, so it'd be that there's a 0.02% chance of seeing our sample statistic. Or more extreme. But the idea is if we had a fair coin, the probability of getting that 75% out only had a 0.02% chance, which is a very low probability. So what we saw was something statistically significant. So this is where we would have a small p-value. And again, we'll talk about what the cutoff is small versus not small, but 0.02% chance, very low. So with that, we get to reject the null hypothesis, because we saw something that shouldn't be happening for a fair coin, or it has a very low probability if it is a fair coin. So this is where we have evidence that our coin is unfair. Evidence for the alternative. So in wording our conclusion, what we're going to do is kind of start with this main statement that's going to be about whether or not we reject the null hypothesis. So for us, we reject the null hypothesis. And then just like we did with confidence intervals in terms of stating like with 95% confidence or 99% confidence, which was it was stating our level that we were working at. What we're going to do here is state the level of our evidence, which is the p-value. The p-value displays the strength of what we're claiming. So like the 0.02% chance is very strong. That shows a very low probability of occurring. So what we want to do is in our conclusions include the p-value. So I'm going to say with a p-value of 0.0002. And then what we could say is there is evidence for, and then what we were trying to prove, which was the idea that we have an unfair coin, or our coin is showing more than 50% heads. So I could say there is evidence that the coin is unfair and shows heads significantly more than 50% of the time. All right, so what I just wrote on this page is a full hypothesis test. So what we're gonna do is go through a few videos, break down how do we set up our null and alternative hypotheses. Then you'll have a video on checking the central limit theorem and building that sampling distribution. And I'm going to keep tying in that test statistic, even though we couldn't work around it, just to be consistent with other resources. Then we'll talk about finding that p-value and making your conclusion and kind of put all of those pieces together.